Okay, so welcome back to this week 4 of the Analysis Random Walks and Groups course. And this week we plan to go more into the analysis side of the course. And I want to talk about this topic called ergodicity of a random walk, which is a notion basically originating from maybe I would imagine it's more from physics, where we want to talk about this notion of chaos. Like, what does it mean to be something that is very chaotic and, let's say, sensitive to initial conditions? And we can formulate this with this notion of ergodicity. And for this purpose, let me revise you a little bit of the kind of limits, the notion of limits that we need for this this notion. So we start from this, let's call it ergodic theory. And we start with this notion of a limit of a probability distribution. So let's say definition, let mu1, mu2, mu3 be a sequence of probability distribution. So they are all functions from ZB to 0, 1, and they are probability distributions. And what we have here with these probability distributions, we can then, if you remember, the definition of probability distribution is that individually all of them satisfy the condition that if you sum over the elements, then the sum is equal to 1. So what you can do is that you can define a limit, the limit of this this sequence of this, the limit of this mu1, mu2, mu3, and so on, is then the limit lim, I would say n going to infinity of mu n t, and we call it mu infinity t at the t equal to zp. And here, provided that it exists. So it is not necessary that when you have a sequence of probability distributions that you actually have an existence for such a limit. So if you just to remind you about the limits notion. So basically meaning that if you take any sequence, so let's say we have our group here, and at every point we have some different probability distributions. Let's say this is one, and then there's another one which is maybe a bit more bigger, then a smaller, and then you have maybe a bit smaller one, and so on. So you have these different heights at each of these points, and what you're asking here is basically when you start to take sequences of this. Let's say at this point t here, over here, this t. And you take, let's say, mu1 of t, and then you have mu2 of t, and then you have mu3 of t, and so on. And you're asking whether this sequence has a limit at this point t, if this limit exists as a real number. So this is a sequence of real numbers. So it might fluctuate. So it's possible that you just constructed a very strange sequence of probability distributions that actually fluctuates a lot, so you don't have this limit. But provided that the limit exists, then we have this notation that we want to use for the limit, which is this mu infinity t. And this is important in the notion of a chaos. So if you remember the notion of total variation distance, so we can have this, let's say, a theorem. So this is, I think, theorem in the lectionals. The current version is 3.26, and the theorem is saying the following: that it's like a characterization whether this has a limit or not. Whether if you want to construct a limit, like so, let mu1, mu2, and so on be a sequence of probability distributions in ZP, then they have a limit mu infinity, which is a probability distribution also probability distribution if and only if the total variation distance mu, let's take n and then mu infinity, these are both probability distributions, this goes to 0 as n goes to infinity. So basically you can just check your convergence just from the notion of total variation distance. So this is like one of the advantages of using the notion of total variation distance, for example, that if you can prove that you have some limiting probability distribution, there is a probability distributions that this sequence of probability distributions mu n approaches, then you have this pointwise convergence. Then you can actually say that this at a given point that you consider over here, for example, like in this picture we have this one, you have this sequence that converges at this point. So I leave this as an exercise. You can try to check the kind of just from the basic definitions, but this is like a really just basic coming into the notion, because if you think about you could use, for example, the L2 identity, for example, to prove this. This is like really just from the it's a sum, finite sum, so it's not a very complicated proof. But then what I would like to maybe then use this kind of definition, then this we can now define let's call it ergodicity of a random walk or a probability distribution. So because when you have a random walk in this course, we are always given some driving probability distribution that defines it. So we say that a probability distribution mu from ZP to 0, 1 is ergodic if if mu star n, so if you take this iterated convolution with itself, so remember this is some sequence of distribution, has a limit, let's call it lambda, which is the uniform distribution in ZP as n goes to infinity. So that's how we define the notion of ergodicity of a random walk. That if this iterated convolution has a limit when t goes to infinity. So let's open this a little bit. So what do we mean by this? So let's kind of definitions and everything that we have here. So i.e., so if we open this up a little bit, this means by the definition by this theorem above, we have that this is the same as the iterated convolution n, and then this lambda going to 0 as n goes to infinity. Okay, so that's basically what do we mean by ergodicity. But let's try to open this up a little bit probabilistically. What do we mean by this this being like a limit? So when you have this convergence to 0, you can remember that if you take this total variation distance, what was this again? So this was the, I think we had it as a maximum of the probability of n of an event A, and then you had the distance lambda A. That was the distance, and then this was over all sets in ZP. So if you have this kind of limit going to zeros, and this maximum goes to 0, thus mu is ergodic if and only if for any A in ZP we can actually prove this this measure converges to the lambda A as n goes to infinity. So that's something you can check from this, but you can now see that, okay, it's a bit like the pointwise convergence, but it's the same kind of idea that you have here, that this goes to 0. So this basically this distance tends to 0. But so you can also like write it like this, that you can take this going to 0 as n goes to infinity. It's no matter which way around you want to put it. But then what's the thing about this? So if you open it into the language of probability, if you remember what this is and this is now here. So this is the, let's first look into the right hand side. So we have the lambda A. So that is, if you remember, just this is the sum of t of A, and then it's lambda t, which was equal to 1 over p. So what this is just the cardinality. So this is 1 over p, and then t in A of 1, which is then I think I use this notation A cardinality over p. So that's like a uniform weight. So the total number of elements in the whole group is p, and then the A. So this that's the kind of probability. But then this one here, the left hand side, you have the iterated convolution. Then if you use the language of probability, so if you have this IID random walk, then this is just the probability of this event x1 plus xn hitting this point A. So that what this here is, so remember this is now the x1, x2, x3 and so on. These are IID, so independent identically distributed random variables with distribution mu, i.e. if you take the probability of xj getting a value t, then this is just mu t. And these are independently chosen from each other. So basically the ergodicity, we have now a way to write this, that the ergodicity of the random walk is just basically x1 plus xn belongs to A. Then this probability of this event, so computing this probability of the event, it's just basically computing the cardinality of A over P, that this goes to 0 as n goes to infinity. So basically no matter what event you choose, you have that this happens for every A, which is a subset of ZP. Sorry, maybe I should put it outside, and it's for any A in. Maybe let's put it here for any A subset in ZP. Okay, so now it's when it's in the notion of a random walk, we can now really look into the kind of intuition behind the chaos. So what it means that, okay, let's say we start to move our random variable. Let's just take the basic example what we had already earlier, which was the mu equals this half Dirac minus 1 and half Dirac 1. Let's take it in, this in, let's say, Z4. For example, I think the, or maybe let's take Z4 is, yeah, that was better. So we have these 4 points over here, and what this gives us is basically a half weight here and a half weight here. So that's what mu looks like. But then when you have a random walk that is choosing these values from 1 and minus 1 all the time, so this is 1, 0, 2 and 3, which is this is equal to the inverse of 1, -1. Then what you have here is that you're basically having this probability of going right and left with probability half. And now that you start to walk, let's say at this phase, so at the first stage, let's say we chose 1 at this stage. And then the next time we choose left or right, so we added the convolution. Let's say in the second stage, we moved in here, for example, at that point, and then maybe next time we move to here at this point. And now you could ask, for example, an event of a probability, for example, let's say we take this event, for example. So this would be our event A. So the set 0, 1. So what you could now ask, that after these 3 steps, what is the probability of hitting this set A? So okay, you had the possibilities of going left and right here. So of course you could have this option as well, and then here you could have come back down, and you could have come back down. Yeah, like this, and then you could have come back down at this point as well, instead of going right. And then there's also these other possibilities. And what you can then see is that this set, the number of times you start to visit there, proportionally, you start to visit there roughly the cardinality of A over P times, which is then cardinality A over, let's say, P, which is then 2 over 4 times, which is roughly a half that you're going to be visiting this set A of the times. Even though you start from this kind of very like general random walk, you can then say that once you start running this, the amount of time you spend in this set, let's call it, let's use another color, this set A at this region, or these 2 points, basically, is going to be roughly half of the time in the limit. We haven't yet seen that this is ergodic, but this is, it turns out that it is actually in this setting, that is an ergodic random walk, that you actually do spend this kind of time in this kind of situation. And so basically, when we start to talk about the notion of chaos, we basically see that if you take any set here, A, you could take any one, okay, I could take this set, for example, over here. Maybe this is a bit messy picture, but I could take any, let's say this set 1, 2, or 0, 1, or 0, 3, or 3, 2, or 1, 2, 3, for example. Then what happens with the chaos is that no matter where you go, no matter which kind of sets you choose, you still have the proportionally that you're in this A over, the cardinality of A over P times inside visiting this set. And that's quite an interesting phenomenon, because, for example, it means that no like region of the space is left like in a different position. That everything is getting basically uniform visiting times, and that's the kind of what in this course we want to talk about, the notion of ergodicity. That it means basically this. In other courses, and I think in other topics, you might see different types of notion of ergodicity as well. So, for example, sometimes you want to talk about the random walk, not visiting everything completely uniformly, like with this lambda basically that we've been using, but it could visit according to some other measure, for example, some other mu. That just means it's ergodic with respect to some other type of maybe a measure that we have in the space. It's very common that the ergodicity is typically with respect to this uniform distribution, and in general in random walks and groups you will see that it's this notion of something called Haar measure that we talk about maybe later in the course, where you have this kind of uniformity with respect to this uniformity over the whole space. And that's kind of like but it's more like a beginning of the kind of getting maybe some feeling about what's going on with the notion of ergodicity. And in the next lecture, I will concentrate on how this ergodicity is connected to the notion of subgroups. So there's a little bit still missing in the intuition that we are not fully maybe aware of like what the consequences of the group theory will be in the notion of ergodicity. And the subgroups later on we will see will allow us to basically decipher whether the random walk is ergodic or not. So it depends on the kind of subgroup decomposition of the group that we are considering, whether you actually have an ergodic random walk with this definition or not. It's quite interesting actually that it's basically a characterization of ergodicity using the subgroups of the group. Okay, so that's all for today, and I'll continue with the subgroups in the next lecture.